Car Crash Analysis Biomedical Engineering presented by Jacob Hanala. To begin, a set of data is collected from the triaxial accelerometers on a Hybrid 3 test dummy that shows the acceleration in G's exerted during a car crash from moments just before impact to moments just after impact. The data from columns A and E can then be converted into a graph to show acceleration in G's as the dependent variable and time in milliseconds as the independent variable. The acceleration has a huge spike at about 120 milliseconds, and then somewhat of a spike at around 270 milliseconds. These spikes represent the jolt on the head, the first impact, and then the secondary jolt that can also be experienced. The first jolt shows a peak at approximately 30 to 35 Gs, and the second jolt shows a peak at approximately 8 to 10 Gs. To put that into perspective, fighter pilots experience approximately 9 Gs at the maximum. Since car crashes contain such radical amounts of acceleration on body parts such as the head, severe injuries can be the result. It is important to note that the unit for acceleration is in Gs in reference to g-force, so the numbers present in the data for Gs is x amount of times the acceleration of gravity near the surface of the Earth, which is approximately 9.8 meters per second squared. Here's a simulation of what a car crash looks like, and it clearly shows the massive change in velocity of the head in such a short amount of time. To show just how much force is being exerted on the head of the dummy, Newton's second law is necessary. The law states that the unbalanced force is equal to the product of the mass of an object and its acceleration. By using Newton's second law equation highlighted in blue, the force can be determined. The approximate amount of force can be found by taking the average mass of a human head as 5 kilograms. Then the mass must be multiplied by acceleration at the very peak of the data on the first jolt at around 32 Gs. Notice how 32 is multiplied by 9.8 in order to convert units in Gs to units of meters per second squared, so acceleration. Then the mass and the newly calculated acceleration can be multiplied to show that the head in the crash test experienced approximately 1,570 newtons, as seen highlighted in yellow. The amount of force that was just calculated is what is experienced at only around 30 miles per hour, but if the speed was doubled to around 60 miles per hour on a road such as a highway or a main road, acceleration would grow to twice the original amount as well as the force. So the amount of force that would be put on the head in the event of a head-on collision into something like a wall would exceed 3,000 newtons. According to Newton's first law, an object in motion stays in motion unless acted on by an outside force. In this image, we can see a car hitting a wall. The car stops and the arrow shows a person about to fly out of the car into a tree. This image is a very basic representation of what would happen if the necessary precautions such as a seatbelt and airbags were not present. Because of Newton's first law, a car crash with no airbags and no seatbelts would result in its passengers flying forward until they met some sort of resistance, which is also an outside force. Many injuries and fatalities can also be caused by various things such as hitting the steering wheel, framework of the car, other cars, buildings, and so on. One thing that we know about car crashes is that a head-on collision into a wall shows significant effects on the car, but little to no effects on the wall itself. The reason for this is that the wall is extremely sturdy and can absorb a lot of the blow without showing signs of damage. However, both the car and the wall are experiencing the same exact amount of force, and this can be explained through Newton's third law. This law states that for every action there is an equal and opposite reaction. In the case of a car crashing into a wall, the force exerted on the car by the wall is the same as the force exerted on the wall by the car, and that can be seen through the force diagrams presented in this image. Here is a new situation in which two cars are colliding head-on. It is different from the wall versus car collision because the wall is static. However, looking at the force diagrams, the unbalanced force exerted on all of the objects is exactly the same. This is all assuming that both car 1 and car 2 have the exact same velocity and mass as each other and as the one in the first situation. Also, this is assuming that both will come to rest. Because of Newton's third law, the force exerted on the wall by the car is the same for that of all the other objects. Additionally, the cars from the second situation are moving at the same velocity and have the same mass as the car in the first one. This is important to note because it shows that the force that the passengers feel is the same for both situations because of Newton's third law. Now that we've covered the basics to a car crash in terms of acceleration, we can talk about the various injuries that can result from collisions. One of the most common injuries caused by a car crash is whiplash. This is the injury to the head and neck area caused by severe jerks to the head. Referencing back to the graph from earlier, there were two large spikes in acceleration that represented the jerks of the head that can be seen in this image. The cause of whiplash has to do with Newton's first law because the head wants to keep moving forward, but the tissue and ligaments in the neck keep the head connected to the rest of the body. This is the outside, unbalanced force that keeps the head from not maintaining constant speed and direction through the windshield of the car. Whiplash is most common in rear-end collisions but can be experienced from T-bone and frontal collisions. One thing to note is that whiplash can also be classified as cervical acceleration-deceleration syndrome, which corresponds with the image in the previous graph because the head jerks one way representing acceleration and then jerks the opposite way representing deceleration. Rear-end collisions can also result in misalignment of the spine and potential paralysis, as well as bone fractures, because the bones and organs go from a constant velocity with zero acceleration to high amounts of acceleration and do not have much time to control the massive change of momentum. One common type of accident is the T-bone collision. This is when one car collides with another one at a perpendicular angle, often resulting in many abdominal tissue tears as well as fractures. The area seen in this image is a target area of T-bone injuries. Additionally, these collisions can result in a misalignment of the spine from the large impact that the spine has to withstand. Frontal collisions are one of the most dangerous and can result in death from ejection straight through the window or into an interior piece of the car, such as the steering wheel. Severe injuries range all the way from concussions to internal organ damage to bone fractures because the passengers' bodies have such great inertia and so much momentum. Because car collisions such as the ones just referenced are so dangerous, modern cars contain a multitude of safety features to help prevent injuries and/or fatalities. These features include seatbelts, airbags, and crumple zones, which are all seen in this image. All of these precautions revolve around something known as the impulse momentum theorem, which states that the change in momentum is equal to the product of the unbalanced force and the change of time. In situations such as car crashes, the amount of force cannot directly be controlled by the manufacturers. However, the change in time of collisions can be controlled, and it is done through the previously mentioned precautionary elements. These safety features increase the duration of a collision and ultimately reduce the unbalanced force, assuming that this is a closed system with conserved momentum. As a result, the force of the impact is significantly diminished. Thank you for watching, and I hope this gives a little insight on how biomedical engineering ties into car crashes.